Okay. Okay, so let's remember what we're doing. We're talking about, what are we talking about? Anybody want to tell me?
The wave equation,
Right.
3 dimensions.
In 4 dimensions? Yeah, R3 cross R. Right, so that's what we did last time. We did wave equation on R3 cross R, right? And then we ended up with this nice, physical interpretation that this is actually expressible in terms of these spherical means. Right? In terms of the spherical means, right? So that was nice, right? There's this physical interpretation, right? And what we're doing today is we're going to take that and we're going to use it to get to solve the wave equation on R2 using Hadamard's method of descent. That is sort of, and we sketched this out last time, right? You take the data for the 2-dimensional problem, and then you change it into data for a 3-dimensional problem. Then you just apply the 3-dimensional problem. You apply the solution. You get the solution for the 3-dimensional problem, and because we've extended it constantly in the third variable, when we take the Laplacian in the third, the terms in the third variable just vanish, right? Because you're differentiating with respect to the third variable. Well, those guys just vanish. That gives us that the Laplacian is going to be 0. That is, that we solve that the solution will solve the wave equation in 2 dimensions, or 3 dimensions, R2 cross R, and that does it for us. Okay, so that's the idea. That's the rough idea. What's going to be necessary is the following calculation. So remember that that this thing is the spherical mean, right? So it's the right. This thing was the spherical mean over the sphere centered at x and of radius t. Okay. So this is the spherical mean operator. Right, and so what's going to be necessary is to consider the question, what is the spherical mean of a function if h is constant in the third variable? So if h, i.e. if h x1, x2, x3 actually equals h of some 2-variable function, right? So it doesn't depend on the third variable. Okay. So, and that just turns out to be a calculation. So let's just do the calculation, right? So. Right. So if we look at the spherical mean at x1, x2, 0, right? The third variable isn't going to matter. By definition, that's going to be 1 over 4 pi, and then we spell out that spherical integration as the integral, the theta, when theta ranges from 0 to 2. I'm sorry, phi ranges from 0 to 2 pi, and theta ranges from 0 to pi. It'll be h of x1 minus t sine theta cosine phi. Comma x2 minus t sine theta sine phi. Oops. have a sine theta d theta d phi. Okay, so this is just the definition of that integral. Okay, so what we do is we break it into two parts. One where theta ranges from 0 to pi over 2, and two and the other part where theta ranges from pi over 2 to pi. Okay, so we just split. This is basically just a calculus exercise. So we split it into two integrals, and then we say, well, okay, now let's do a change of variables. We let r be sine theta, right? So theta equals in the first one, theta is going to be. Theta is going to be arcsine of r. Okay, and in the second one, theta is going to be pi minus theta is going to be arcsine of r. Okay, because we're going from pi over 2 to pi. Okay, so that's how that works out. Okay, so this is for the first one. In integral 1 and integral 2, we use this substitution. In both cases, it turns out that you get the same integral. So you get the integral from 0 to 2 pi, integral from 0 to 1 of h of x1 minus tr cosine phi x2 minus tr sine phi, and then we have sine theta, which is r, and we have cosine, and then we have d theta, which is going to be the derivative, which switches to the derivative of the arcsine. So you get this 1 over the square root of 1 minus r squared dr d phi. Okay, so in the second case we do get a minus sign on it, but it's going from, we have to switch the order. We have to switch the bounds anyway. So that cancels out. Okay, that's good. It's a Calc 3 exercise. Okay, and now we use more Calc 3, which is we use polar coordinates, right? So we've got this r cosine phi, we've got this r sine phi, right? So now let y equal r cosine phi, r sine phi, right? And we end up with the integral. So I'm sorry, we get two of them. They're the same, so we get two of them. So in the end, we get 1 over 2 pi, integral from 0 to 2 pi. Integral of that thing, right? So now we switch back. Yeah, we switch from the polar coordinates back to the Cartesian coordinates. Okay, and we get 1 over 2 pi, the integral of x minus ty, 1 over the square root of 1 minus absolute value of y squared dy. Okay, over the disk of radius 1. So so that's what we get, right? Okay. So right. So let me just write that out. We get that the spherical mean at this point equals the integral of h minus ty dy over square root of 1 minus absolute value of y squared over the disk of radius 1. Okay, so this is what we called last time the weighted disk mean. We didn't call it the weighted disk mean. We called it something else. What did we call it? We called it the weighted average over the disk. So weighted average of h over the disk of radius t centered at x. Okay, and we denoted this by m sub t h at x tilde. Okay, so this is nice, right? This is why we have this idea at all, right? This is why we even have this idea, right? If you take a function on R3 and take its spherical and it's constant in the third variable, and you take the spherical average of that function, then that's the same thing as taking the weighted disk average of the two-dimensional function at that point. Okay. Right. Okay. So that's the lemma that's going to be useful. That if if h is if h of x1, x2, x3 equals little h of x1, x2, then the spherical average of h at x1, x2, x1, x2, 0 is going to be the weighted average, the weighted two-dimensional average of little h at x1, x2. Okay, so now we'll use that to get the solution. So now we do the method of descent. Okay. So method of descent says that okay, suppose we start off with f and g that are in the Schwartz class on R2, right? And so actually, let me write up the theorem. So let f and g in R2 be the initial data for the Cauchy problem. For the wave equation. The wave equation on R2 cross R. Then the solution is going to be just the same thing as before, but we're going to take with the we're going to use the weighted average rather than the spherical average. Okay, and the way we're going to get this is like we sketched out. So we'll so take a bump function. What's called a bump function, eta, on that's in the Schwartz class on R. Okay, and the bump function is going to look like this, right? It's going to be between, for fixed t, so fix a t bigger than 0, and then the bump function is going to be 1 between negative 3t and positive 3t. Okay, and then you know it declines after that. Right? So it's Schwartz class, so it's decreasing rapidly. Okay, so now we take we go from the two-dimensional problem to the three-dimensional problem by we let f flat x1, x2, x3, x2, x3 be just f at x1, x2 times the bump function at x3, right? So, you know, as the third variable goes from negative 3t into positive 3t, the function is constant, right? We just take our data and we extend it flat, you know, for a certain interval, and then it drops off. Okay. Similarly for g. Okay, right. Now, so here's the picture. Here is R2, okay, and here is R3. I'm sorry, here's R1, right? So our initial data, right? Our initial data is on R2, and then we extend it constantly, right? So like you have some initial data of how your wave looks, right, at time 0, and then you just extend that constantly for a period of time, and then let it drop to 0 afterwards. Okay. Now, recall. So now let u of xt. No, let u flat of xt be the solution. So this is, you know, x1, x2, x3 t be the solution from before. We know how to solve the equation on R3 cross R. Solve it. Okay. We get some solution u flat, right? So u flat, right? So remember that this is R2 and this is R1. Remember that u flat is determined by the data at the base of this backwards light cone, right? And that data, as long as we stay for absolute value of t less than big T, u flat xt is constant in x3 for all x3 in size smaller than t. Right? So like, let's say this is t. This is negative t. 3t is out here. Right? And here is our t. right? T is like this, right? Then, as the radius of the base is t. So as long as our little t is smaller than big T, then we're within this negative 3t. We're within the negative 3t, positive 3t interval, right? And so when we move this way or that, we're not changing. The data is constant, right? And that means that the solution is constant in that third variable. Okay. Okay. So right, and so as we said before, when you apply the Laplacian to that, well, the derivatives with respect to the third variable are going to be 0. So we get that the sum of the second partials in the first and second variables are equal to 0, right? And so this u x1 x2 t that we define as u flat x1 x2 0 t is a solution to the wave equation for t in absolute value smaller than big T. Is that all right? Right. Okay. Okay. Right. Okay. So that gives us a solution up to big T in time, right? But the thing is that T was arbitrary. And if we take a T prime that's bigger than T, well, then the solution for the big one agrees with the solution for the smaller T for T smaller than the smaller T. Does that make sense? Like if we take a bigger T, right? We take a second T, T prime, right? T prime, right? As long as we take the T's that are satisfy the earlier T, satisfy original T, well, the solution is going to be the same thing, right? Because we're still going to average over the same data, right? So those guys are going to agree where the initial guy, where the use of original T was defined. I should call this T2 and T1. Okay, so like, right? So that means that as we take larger and larger T's, the solutions are going to agree with the smaller T's. So we're just expanding our solution as we can let T go to infinity, and we get a solution over all time. Okay. So thus we obtain a well-defined solution for all T. Right. Call it U T1 x1 x2 T. Okay. Right. Well, that solution, U x1 x2 x1 x2 t is just U flat of x1 x2 0 t, but that is expressible in terms of the spherical means of F flat and G flat, right? This is what we worked out last time. X1, x2, 0, 0. plus t mt g flat x1, x2, 0. Right? That's what we worked out last time. And from the calculation we did at the beginning, right, this is the same thing as d dt t m twiddle t of f x1, x2 plus t mt twiddle of g x1, x2. Right? Because f flat and f, f flat is just the extension. Is just the extension of f in the third variable, and it's within the bounds that we're looking at, it's constant. Okay, so this is good, right? So we get that. So that's the end, right? We've got the solution to the wave equation in R2 cross R by just sort of using the solution in R3 cross R. And this, the comment that they make is that, well, this kind of shows the difference between two-dimensional waves and one-dimensional waves, in the sense that the light cone here, if we're thinking about Huygen's principle, for R2, right? What this says is that if we're at a point x comma t, this is x comma 0 here. If we're at a point x comma t, then the solution depends on the average of the function in the disk of radius t. So this length is t, this radius is t. The disk depends on the average of the function, but not on the boundary anymore, right? Not on the boundary, like in the spherical case, but the average on the whole, over the whole disk, right? Right. So it depends on that, and again, sort of taking things conversely, right? If you have data at this point, then it affects, right? What does it affect? It affects everything in here, right? It doesn't just affect the edge as it did in the three-dimensional case. It affects everything in here, right? And so they say, look, if you turn on a light, if you turn on a light just for a moment, then people at some millions of years away, for a moment, they're just going to see that one flash, right? But if you drop a rock in a pond, then the people at the edge of the pond, starting at some time, are going to see oscillations forever, basically, right? So that's the point here, right? That it doesn't just affect the boundary. So there's a difference between the two-dimensional case and the three-dimensional case. And in general, there's kind of a phenomenon that the odd dimensions and the even dimensions behave differently. A phenomenon in Fourier analysis that the odd dimensions and even dimensions the cases are quite different. Okay. Is that okay? You guys got that?
Mm-hmm.
Okay. So
and in one dimension, it's more similar to the three-dimensional. When we were looking at D'Alembert solution, would that be more similar to what we just did, or? It's actually different because you remember D'Alembert's solution says you're going to take the average of the points at the ends, mm-hmm. but you're also going to take the average of the velocity data over the interval, mm-hmm. right? So in fact, it's more similar to the second. Okay. Yeah. Okay. So I am going to skip the part on Bessel functions and parity. They talk a little bit about, remember, if f is radial, then the Fourier transform is radial,
right? There was this comment that f radial, it's a calculation that if f is radial, then f hat is radial. And they look at, radial, of course, means that f is just some function of the size, right? Some function of the size, right? So here, f hat would also be some function of the size. And they look at the relation between these slices of your function, and this part of the text is not really. I think this is simply included to show that there's again like a difference between the odd case and the even case. That the odd case is actually more complicated than the even case. So I don't want it. I think let's skip that. It's just calculus. So you can read it. Please read that part yourselves. Okay. So rather than do that, let's go on to the Radon transform. Something that I have some fondness for. The Radon transform. Yeah, I actually have one paper that's related to the Radon transform. Okay, and you'll kind of get the background for that paper. Okay, so first, we just sort of introduce like various forms, various versions of the Radon transform. First one, you have some function rho on the plane. Okay, and L is a line in R2, and we define x of L. X of rho of L to be the integral of rho over L. Okay, so so you have some you have R2, you have some line L in R2, and you have some function on R2, and you integrate the function over the line. Okay, and that's x of that function over that line. Okay, and this thing is called the X-ray transform. The X-ray transform. The reason it's called the X-ray transform is because it corresponds to X-rays, right? So like if you have a slice, so this is like the slice of a person. This is like a slice of the abdomen of the person, say, right? And right, so you have inside the person, right? It's not uniform. Some parts are more dense than others, right? Some parts are more dense than others, and so you consider that density to be the function, right? So here we are in R2. Here's the slice of the person, and you have some function rho, which is like the density of the material at each point. Right, and you want to know what the density is inside the person. Okay, and so you send X-rays to the person, right? And what the X-rays do is basically they give you data on the other side, right? So you've got your X-ray film over here, right? And based on the color, based on the intensity of the picture here, that gives you information about how much material it passed through on the way. Okay, so it's basically like taking an integral. So the X-ray
is an integral, is a bunch of integrals of your, like each point, right, gives you the integral over some line, right? It gives you the integral of the density function over that line, right? Right. And the idea of the Radon transform is, can you figure out the value of the density at every single point from the integrals over the lines, right? And the answer is, of course, no, if you just take one X-ray, right? That's like, it's like if somebody gave you a magic square and they said, I'm going to give you the sums of only the columns. Can you tell me the values inside the square? The answer is no, right? But for CAT scans, right? So for CT scans, what you do is you take multiple angles, right? So you take the integrals along this way, you take the integrals along multiple ways, right? And the question is, the mathematical question is, if you have the X-ray transform, if you have the information for the X-ray transform along all lines, well, it should be possible to get back the original function, right? To recover rho from this data. Okay. Right. Of course, in reality, you don't want to take all lines, because that would mean that you irradiated your patient an infinite number of times, and they'd be dead. Okay. But in reality, what you do is take it from a limited number of angles, and then you do some approximation. Okay. So that's the X-ray transform. It is one form of the Radon transform. The general Radon transform is defined like this. So we'll talk about the Radon transform on R3. Okay. On R3, what you do is kind of similar, right? So you have some function on R3. You define for each plane, right, for each affine plane, that is, it doesn't have to go through the origin, P in R3, you define the Radon transform of the function at P as just the integral of your function over that plane. Okay. So, yeah. So, and in general, the Radon transform, when we say Radon transform, it means that you're doing it, so this could be like in Rn, then you do it in the n-1 dimensional subspaces, and you integrate over the n-1. So Radon transform refers to codimension, integration over codimension one hyperplanes. And then X-ray transform always refers to integrating over lines. Okay. And if you're doing something between, then you have something called the K-plane, the K-plane Radon transform. So like if you're in Rn, but you're doing it on if you're in R10 and you're doing it with like two-dimensional planes, then you'd say the two-plane Radon transform in R10. Okay. Yeah. So interestingly enough, all this theory was worked out way before the application. Radon did this in 1908 or something like that, and another man named Funk around maybe even before that. And then it's only in the 60s that a physicist, kind of an interesting person, untrained, like somebody without much background, without proper training, but he came up with this idea, and I think he was an electrical engineer or something like that. But anyway, so this fellow Cormac, not Cormac, in the 60s, came up with the idea of the CAT scan machine, and then brought it, made it into reality. Yeah, so only many years later did they come up with the application. Okay, Okay, so, okay. We only have 5 minutes left. I'm slowing down somehow. I hope I don't slow down too much. Because there's going to be that 1 week where I miss 2 classes. So, but I think we're still on schedule. Okay, so some preliminaries, not that interesting. So one, we parameterize. So we're going to be doing the Radon Transform in R3. Okay, but the theory, you can do this in any dimension, and you can do it for things of whatever codimension you like. We parameterize the planes in R3 as follows. We think of them as as the sphere in R3 cross R. Okay. In the following way, so for each gamma comma t in S2 cross R, so you have S2 here, right? And you have some gamma. Okay. You have some direction in R3, and you have some number t. Okay. What you do is you take gamma and you scale it to t times gamma. Okay. And then you take the plane that's orthogonal to that. Okay. The plane that passes through. So let pt gamma denote the plane x in R3 such that x dot gamma equals t. X dot gamma equals t. In other words, it's going to be all vectors x where the dot product of that against gamma gives you t, right? So that the scalar projection is t, right? In other words, all vectors whose terminal points lie in the plane that's orthogonal to this, for which this is the normal vector, for which gamma is the normal vector, and it passes through this point t gamma. Okay. Okay. So then, so for SF in the Schwartz class, we define the integral of f over that plane as the integral of f of t gamma plus u1 e1 plus u2 e2 du1 du2 as u and u2 both range over R, where gamma e1 and e2 form an orthonormal basis of R3. So you take any orthonormal, right? So the picture is, right, we have our gamma, right? We have our gamma, and then we take two vectors that are perpendicular to it, right? We take, some vector that's perpendicular to it, and another vector that's perpendicular to those guys, right? We make an orthonormal basis. We use e1, e2, and we just slide them over here, and we take, t. Whoops. We go to t gamma. We go to t gamma, and then add on linear combinations of e1 and e2 to get the entire plane. So that's how we'll calculate the integral over the plane when we're doing the Radon transform. It's easy to see that the above is independent of choice of E1 and E2. Right. If you choose any two other guys, you can. It's going to be the same. And what's going to be one thing that's going to be useful for us is the observation that the integral over the plane, the integral over R3 is going to be the same thing as the integral over, so for each fixed gamma in S2, the integral over this is going to be the same thing as if we fix a direction gamma, and then we take integrals over all planes in that direction. So we integrate over pt gamma, and then we let t range from negative infinity to positive infinity, right? So we're just splitting up R3 into a stack of planes, right? Right. This is the integral over the plane passing through t gamma with gamma as normal vector, and we let t range from negative infinity to positive infinity, right? And so that gives us the entire space R3. Okay. Okay. And the proof of that is just a simple calculation. So yeah, proof just a calculation. So what we're going to be dealing, the way we're going to think about the Radon transform is the following. For f on R3, then for t comma gamma in R cross S2, we define Rf of t comma gamma as the integral of f over the corresponding plane. So we're going to think, the main thing you want to get out of this is that Rf is a function on planes, but we're going to split the world of planes into R cross S2. Okay. So we're going to think of it as a function on R cross S2. It's got these two variables, and that will be important. It's kind of an important way, a useful way of understanding how the Radon transform works. Okay. Notice that back here, no, somewhere. Notice that P of t gamma is the same thing as P of negative t negative gamma, right? Because if you have gamma in this direction and you have negative gamma in that direction, well, the plane with scalar projection at t is the same thing as if we go in negative gamma direction and take negative t, right? So really what we're thinking about is this thing, modulo this equivalence that p of t gamma and p of so t gamma is equivalent to negative t negative gamma. Right? So you make a quotient of that. Okay, that's it for today. Next time there's an exam, right? Yeah. Next time there's an exam, but the time after that we'll talk about how to invert the Radon transform. right? How do we get back to the original function from the Radon transform? And that will involve the sort of central fact called the Fourier projection theorem, Fourier slice theorem, which relates the one-dimensional Fourier transform in the first variable of the Radon transform to the three-dimensional Fourier transform of the original function. So, yeah. Okay. Look forward to it. It'll be fun. Unfortunately, that's all we do with the Radon transform. That we're gonna drop it right after that. So.
What motivated the Radon transform? Why?
Yeah, I don't know. I mean, it's kind of an obvious question, right? Like if you have a bunch of integrals, it's like a magic square problem, right? If you know the sums over all rows and all columns, can you tell the original thing, right? That's kind of an obvious, like a child's question.
Yeah.
And then you apply that child's question to this, right? To the plane or to space or whatever.
Did the inversion of it, was it developed like at the same time as the definition?
Yeah. So in the early 20th century, right? But the application didn't happen until 60 years later, 50 years later, 50 some years later.